Hi, welcome back to the Student Machine Learning Coalition Intro to Machine Learning course. So you just finished the prerequisites, now it's time to move on to the main thing, machine learning. Hi, my name is Michael Lutz. I'll be returning as your instructor today. Let's get into it. As always, we're going to start with the table of contents. So first, we're going to discuss the types of machine learning before getting into the difference between classification and regression tasks. Next, we'll discuss the terminology of supervised machine learning, and then we'll discuss training models and their pipelines. Fifth, we'll discuss the evaluation of models, before finally the bias variance trade-off and the kind of difference between overfitting and underfitting. All right, let's get into the types of machine learning. Now, one way to clearly think about what the different types of machine learning are is to simply look at the data sources and the outcomes. Let's start with the outcomes. There are often three different outcomes you want to achieve when you're using machine learning. There are more, but these are the three basic ones. The most common is predictions. We want to use historical data coupled with an algorithm to predict what's going to happen if we're given future data, but maybe not the label. Now, what does that concretely mean? That means, in the sense of supervised machine learning, we'll have some data from the past with a certain label or a ground truth that essentially tells us what we're going to be predicting when we're given the same data in the future, just without that ground truth variable. Unsupervised learning, on the other hand, doesn't use any ground truth variables or labels. Rather, it just looks at a data set and tries to find some sort of patterns to extract from. And so oftentimes this will refer to something called clustering, or grouping together data points based on how similar they are. Now, on the other hand, you have actions, which can be a result of reinforcement learning algorithms. In this sense, you can think of an AI playing chess or an AI playing Snake, where you have a dynamic scenario where there isn't necessarily a data set, but still there's an algorithm that learns based on how to best optimize that scenario. And so instead of predictions or clusters being returned, you have actions. Now, one thing to keep in mind is that in today's course, in this lecture, we're going to be focusing on supervised learning. And the reason for that is because supervised learning is generally what you think of when you think of predictions, when you think of Kaggle competitions or data science. And so it's this really big ubiquitous field that we're going to be exploring throughout the rest of this lecture. However, if you are interested in any of these other topics, definitely feel free to explore those. So now we're going to move on to classification versus regression tasks. So there's two main types of supervised learning. There's classification and regression. Classification is pretty simple. We're simply predicting what class or category something belongs to. In other words, we could be predicting whether somebody has a deadly disease or not. Yes or no. 0 or 1. That's binary classification. You can have more than just two categories, however. For instance, you can predict a flower species type. There can be multiple flower species, and your algorithm has to choose between, say, 3 or 4 and predict one of them. An example of this is called multi-class classification. Okay, on the other hand, you have something called regression, which instead of predicting a category, predicts an actual continuous number in a continuous fashion. For instance, you can have housing price predictions, which won't simply be a 1 or a 0, which will actually instead be something like maybe $100,552 or $2,542,000. You see, these are much different than predicting, say, the day of the week or a type of flower species. Now, on the other hand, you can have predicting monthly returns. That's another numerical type. You can also predict type. You see the commonality between numerical types. They're all numbers that don't necessarily fit into a class easily. An easy way to tell the difference between categorical and numerical supervised tasks is to simply look at the amount of differences between the potential predictions. If there's a ton of possible values, it's likely going to be numerical. If there's, say, only 5 potential values, it's likely going to be categorical. Okay, so now that we know that difference, let's move on to the terminology of supervised learning. This is what we call a data frame when we're working with pandas. We can also call it a table, You can also just call it a database. Oftentimes, and in this course, we'll refer to this as a data frame or a matrix. Now, at the top of this matrix or data frame, you'll see the different, you'll see a top row which shows the different features. And so, for instance, aircraft engine class is a feature, route text is a feature, speed, heading, altitude, so on, so forth. Now, if we are predicting the distance total that the aircraft travels, then that becomes our ground truth, or label, or target value. It's the thing that we're going to be predicting. In mathematical terms, we often refer to this as y, and it's oftentimes lowercase because generally it's only one value. On the other hand, x, which represents pretty much everything else, is generally uppercase. Note for this presentation, we didn't really make much of a distinction. Just know that sometimes you will see y as undercase. So don't be alarmed if that's the case. All right, so now that we know the different types of machine learning, we know the different types of supervised machine learning, and we know the different terminologies that refer to supervised machine learning, let's actually get into what this will concretely look like when we use machine learning techniques. And so this involves the training pipeline. Let's understand what the process is and how we get from point A to point B. Oftentimes, our pipeline includes splitting the data into training and test sets. Let's look at the training set first. The training set is what we use to actually train our model. And so it'll be roughly 60 to 80% of our entire data set. What it will have is it will have both X and Y values. In other words, it will have all the features and it will have all the label values. And this is what's going to be used for our algorithm to learn the patterns that connect X with Y. Now, if we move to the test set, we don't have any Y. That's because we actually want to use the model that we trained on the training set and see how it performs. And so we're going to leave out the Y for now, even though we do have the true values, and simply run our algorithm only on the features or the X values and see how well it does. The question is, how do we know how well it does? Well, that brings us to the next topic, and that is evaluating our models. How well did we do? We can look at the residuals, which in regression is the way that we determine the difference between the absolute actual value, the ground truth, and our predictions. If we want to turn our residuals into actual metrics we can look at or train our models off of, which we will then call loss functions, we can do something called the mean average error or mean absolute error. In this case, we simply take the sum of the absolute values of the residuals and divide this number by the number of points. In other words, we're taking the absolute average error. Now, this can be a very simple, intuitive way to look at error because it's just easy to interpret it. If you see that the average error is X, you can kind of get a sense of how accurate the model is. But it doesn't tell the full story. The full story oftentimes includes scenarios where your model predicts well on certain points of the data, but it predicts really, really bad on other points of the data. And so overall, your mean absolute error might be pretty decent. But in reality, if you're missing those points, you might be missing some key data points or key patterns in the data. And so one way we try to combat this is using something called the mean squared error. And so this simply takes the sum of the squared values of the residuals and divides that by the number of points. Now, this obviously doesn't need absolute value because you're taking the square, but the main issue with this one is it's a bit hard to read. We can train our models off of this using this as the loss function, but if you were to say somebody, the mean squared error is blank, it would be kind of hard to understand. And so finally, that brings us to our last error metric, the root mean squared error. It's kind of a marriage of both worlds in the sense that it's interpretable because the metric is going to be in a scale that people can understand. If you're to look at the units wouldn't be squared, But on the other hand, it also doesn't lose out to scenarios where your model predicts really, really bad on certain scenarios or certain data points. And so that's the advantage of root mean squared error. So those were some regression metrics. If we move to classification, we've got an entirely new array of metrics to use, the simplest of which includes simple accuracy. And accuracy is often a term that's just thrown out here and there, but it actually has a very specific reference when we're calling accuracy in the machine learning space. And that is a common metric that involves number of true predictions divided by number of actual predictions overall, total predictions. And so this tells you how many of the predictions you got right. This is simple, it's very easy to interpret, but like mean absolute error, it doesn't necessarily cover the entire picture. Now, an easier way to look at the complex relationships is ironically called the confusion matrix. Trust me, it's not actually that confusing. So we can look at the graph on the right. In this case, you can predict either yes or no. It's binary classification. And in this case, we've got 50 predictions in which the actual value is no, and we predicted no. Perfect, we're correct there. And you've got 100 values in which we predicted yes, where the actual value is also yes. We're doing great. But there are some scenarios in which we predict no, but the actual value is yes. There are 5 of those. And there are some scenarios where the opposite is true. The key difference between this and what accuracy would look at is that there are different distributions of when we predict no when the actual value is yes, as compared to when we predict yes and the actual value is no. It's 5 to 10. Those are different numbers, and those will play key differences in what the actual accuracy value will be. For instance, if we've got a data set which has 100 dogs and 1 cat, and our model is a very simple model that just predicts dogs every single time, no matter what the input is, on that data set, it's going to get some very, very, very high accuracy, close to 99 to 100%. But obviously, that's not a good model, because if you were to give a different data set, for instance, 50-50, it's going to get a 50% accuracy. So looking at the data set and looking at the confusion matrix gives you some insight as to maybe your findings aren't super great. But also, it gives you some very useful insight as to what you can do to improve your model. For instance, maybe you really, really don't want predictions where you predict yes, but the actual value is no. You can do some tuning to try to minimize that. And the actual terminology for what we've been just discussing is the difference between false negatives and false positives. False negatives incorrectly predict negative, and the opposite is true for false positives. Note that these categories refer just to binary classification tasks like the one we were discussing. However, a confusion matrix can be used on more than just a binary classification task. It can be used, say, if you're predicting days of the week or the types of a flower. You can do that. But if we do want to actually look at numbers that are similar to accuracy for binary classification tasks, there is a very popular metric we can do for that. And that metric is called F1 score. F1 score is a score that ranges from 0 to 1 that kind of accounts for scenarios in which we're really, really, really bad at one category, but we're really, really, really good at another category, like the dog-cat scenario. But if you are really bad at predicting one category, it brings your overall score down. And so F1 score is often useful for imbalanced data sets. And if you want to know how it works, it's split up into 2 key subfactors. First, recall. All you need to know about that is higher values of recall, which also range from 0 to 1, mean you have less false negatives. For precision, the higher value you have, the less false positives you have. And so both recall are just made of summations of true positives divided by true positives plus either false negatives or false positives. You can kind of think about what that would look like. And so F1 score simply takes the harmonic mean. That means that if any one of them is low, the overall value of F1 score is going to be lower. Okay, we're moving on to the final part of this lecture, and that's the difference between overfitting and underfitting, or the bias-variance trade-off. In an overfitting scenario, you've got a model that fits very, very well to the train set, but really badly to the test set. In other words, it doesn't generalize enough. Underfitting, on the other hand, generalizes too much. But let's actually look at these overfitting, underfitting examples concretely. On the left hand, you have underfitting examples on both regression, classification, and deep learning scenarios. Don't worry about deep learning right now. We'll cover all of that in future lectures. For now, pay attention to regression and classification. In regression scenarios, for instance, if you use linear regression on a curvy dataset, then you're not really fitting to the actual pattern enough. You're not getting that curve in your model. On the other hand, if you were to do something that was severely overfitting to the data, you might end up with something that's the top right corner of this little graph, where you're fitting to every single drop, every single movement in your train set. And so when you actually predict this on an actual data set, on your validation set, you're going to end up with some very, very, very varying data. In other words, it's not going to be super accurate because you've overfit. The best scenario for regression is the middle. Likewise for classification. Another way to look at this is the bias-variance trade-off. Bias looks at how much your predictions vary from the target value. Variance looks at how much predictions would change if different training values would be used. Now, the optimal scenario is low bias, low variance. That means you've got pretty much no underfitting, you've got no overfitting, you're just perfect. But in the real world, oftentimes this isn't the case. You'll have scenarios where you've got high bias, low variance, and high variance, low bias, and hopefully not high bias, high variance, but that does sometimes happen. Oftentimes, you'll be forced into a trade-off between bias and variance. In other words, you have to trade between overfitting and underfitting. Now, making this decision is no easy task. Oftentimes, you'll have to consult with an ethical analyst. For instance, if you're looking at healthcare predictive algorithms for disease classification, you have to look at the harms of false positive, false negative, so on and so forth. And you have to look at the harms of having high variance and having low bias. To make these decisions, just consult domain knowledge. That's often the key solution to many AI problems. If you know more about the problem, the easier it is to make decisions on making your algorithm. Okay, hopefully you understood a bit more about bias and variance, and hopefully you understood a bit more about the basics of machine learning in a concrete manner. We're going to get more concrete as these lectures go on. The next lecture is going to be on linear regression, which is one of the most simple ways you can do machine learning. Hopefully you enjoyed this lecture. I hope you're excited for the next one. See you later.